morning, my dear friends. Today, I would like to explain about the CDF and probability distribution and its properties. See first, CDF, cumulative distribution function. How it expressed the values and expected value of it, and what are the properties of it. See, we need cumulative distribution function. The cumulative distribution function CDF f of x for a discrete discrete x gives for any specified number x the probability of p of x greater than or equal x less than or equals to x. It is obtained by summing the PMF P of y over all possible values y satisfying y less than or equals to small x. The CDF of a continuous random variable gives the same probabilities P of x less than or equals to x where a is minus infinity obtained by integrating the PDF P of y between the limits y and x minus infinity and x where the cumulative distribution function. What is the main by the definition of a cumulative distribution function? The cumulative distribution function f of x for a continuous random variable x is defined for every number x by f of x is equals to p of p of x less than or equals to x that equals to integration minus infinity to x f of y of dy. For each x, f of x is a area under the density curve to the left of x. This is illustrated in figure 4.5, where f of x increases smoothly as x increases. You can observe the graphs of a probability distribution function graphs and associated with which is associated with cumulative distribution function. And coming to let x let x the thickness of a certain metal sheet have a uniform distribution on a comma b. The density function is shown in figure. You can observe the probability distribution function for a given distribution for given uniform distribution, that is which is shaded area is f of x and which is not shaded area is given the before the graph, and after the graph it is shaded area is f of x. See where for x less than a f of x is equals to 0, since there is no area under the graph of the density function to the left of such an x. For x greater than equals to b, f of x equals to 1, since all the area is accumulated to the left of such an x. Finally, for a less than or equals to x less than or equals to b, f of x is equals to integration minus infinity to x f of y dy, which f of y in the graph is which is represented with 1 by b minus a, that is which is simplified by 1 by b minus a integration of 1 is y, that is which we have supplied is x minus a by b minus a. The entire CDF if f of x equals to, see you can also observe the graph of a cumulative distribution function for a uniform distribution. See, using f of x to commutate probabilities. The importance of this CDF cumulative distribution function here, just as for discrete random variables, is that probabilities of various intervals can be computed from a formula for a for or table of f of x. Proposition: let x be a continuous random variable with probability density function f of x and CDF of f of x. Then For any number a, p of x greater than a is equals to 1 minus f of a. This is the way f of x is computed to probabilities, where you can observe in the given figure where commutating P of P of A P of A less than or equals to X less than or equals to B means from cumulative probabilities. This is different from what is appropriated for a discrete integer valued random variables. Here we can take examples such as binomial or Poisson. Binomial random variables or Poisson random variables. Illustrate the second part of the proposition. The desired probabilities is the shaded area under the density curve between A and B. It is equals the difference between the two shaded cumulative areas. And where see you can wait a minute. See, there is a solution. The probability that load is between 1 and 1.5 is f of function of 1.5 minus function of 1 is 0.297. The probability that the load exceeds 1 is p of x greater than 1 is equals to 1 minus p of x less than or equals to 1 minus f of 1. Here, where once this cumulative distribution function has been obtained, any probabilities involving x can easily be calculated without any further integration. Obtaining f of x from f of x. The for x discrete, the PMF is obtained from the CDF by taking the difference between two f of x values. The continuous analog of a difference is a direct shift. Proposition: if x is a continuous random variable with PDF f of x and CDF f of x, then at every x at which the derivative f of x exists, f of x equals to f of x. See, you can also see the example for the given when x has a uniform distribution, f of x is differentiable except at x equals to a and x equals to b, where the graph of f of x has sharp corners. Percentiles of a continuous distribution. When we say that an individual test score was the 85th percentile of a population, we mean that 85% of all population scores were below. That score as 15% were above. Similarly, the 40 percentile is the score that existed 40 of the all scores and existed by 60 of all scores. This is the way that percentiles of a continuous distribution also work. Here you can also observe the shaded areas which you can illustrate the definition of the percentiles of a continuous distribution. Means 100th percentile of a continuous distribution random variables is shaded in terms of having variable. The CDF of sales for any x between 0 and 1 is what is expected value of common distribution function CDF for a discrete random variable x. E of x was obtained by summing x into p of x over possible x values. Here we replace summation by integration and the PMF by the PDF to get a continuous weighted average. Definition: the expected or mean value of a continuous random variable x with PDF f of x is mu x equals to E of x equals to integration minus infinity to infinity f of x dy. See, you can also see the example of expected value of the cumulative distribution function. When the PDF P of x specifies a model for the distribution. See, this is the End of this presentation, which is about the CDF and its properties. Thank you.